moving on to our one session before last with Carl. Carl, if you are with us, can you say hello?
Hello, John. Can you hear me?
Yes, we can. Wonderful. You are with us. Carl, welcome. I'm pleased to have you join us. Before I hand over to you, I would like to give the audience a little bit of background. You are the CTO at Blue Nova, another company manufacturing batteries solutions in Africa, based out of South Africa, and you've been with the company now for 5 years. But I was impressed when I prepared this session. Carl, you look so young, and yet you have more than 30 years experience. Is this true?
I guess so.
Okay. So my
Look at
information
my
was
hair. I'm a bit
correct.
older than the picture. I'm a bit older than the picture you've got there.
Okay.
But yeah, no, it's true.
Anyway, so you are bringing us like a wonderful background in engineering, communications, technology. I've seen you've been leading the company called Rotec Radar Systems prior to Blue Nova, among others. And you're also a fellow of the South African Academy of Engineering. So I think this is more than enough to explain to the crowd your background and expertise with the topic of today. And before, here we go, I'm going to give you the controls so that you can start sharing your presentation, and we are all ears to hear about your topic today.
Okay, I'm just going to have to figure out how to
It's the
share
green button
this.
that says share screen, and then you need to select your presentation.
Okay.
There we go, it's coming.
Are we there?
Very good. Yeah,
Are you seeing it?
can see your presentation. Yes.
Okay. All right. So let me start. All right. So it's still morning. It's a good morning to everybody. What I'm going to try and do today is to just share some concepts on sizing of batteries. It's a complex domain and it's very highly dependent on the context of a specific implementation. So I can unfortunately not present you with a magic silver bullet or a formula to get the best answer. But I can, however, share some concepts with you to give you some ideas and thoughts on what to consider when you size a battery. So I'm just going to basically give you a very quick introduction onto base systems. I think previous speakers have covered that sufficiently. We'll talk about key drivers for sizing, looking at economic considerations. Then it's already been covered, but we will also briefly touch upon the strategies for extending the battery life, because it's an important consideration in sizing. We'll talk a little bit about battery augmentation, and I'll cover two use cases in terms of backup power and energy arbitrage, with some conclusions and recommendations with a quick example of one of our installations. All right, so you basically know what a BESS consists of. It's basically an inverter with a battery pack, a BMS, and most probably an EMS, a cooling system, fire suppression system, access control system, a UPS, and emergency stop with internal electrical distribution. And typically, these batteries or systems are used for grid support, renewable integration, peak shaving, arbitrage, and backup. If you've got off-grid microgrid environment, it obviously will do sort of exercise of providing power to the user. So yeah, at the end of the day, proper sizing for such a battery is absolutely crucial for economic viability and performance. If you install a battery that's too small, there won't be enough capacity when required. If it's too big, you're paying for something that you're not using. All right, so what are the key drivers considering sizing? So obviously, to start with, and it's been mentioned by other speakers before, you need to look at the energy demand profile. You need to understand the energy consumption pattern. That's a very crucial starting point. Without that, you don't know where to go. Then, obviously, in the renewable energy environment, you've got fluctuations in the energy provided by wind or solar, and the battery can then compensate for those fluctuations. But it also has a sizing implication. Then, when you've got a base that you're using to try and manage voltage and power loss, and sizing of the battery is very important. Then, obviously, economic considerations. You've got to look at upfront costs, operation and maintenance, and then the expected return on investments. Nobody will buy a battery unless that return on investment is clearly defined. Then you also have to look at degradation and lifetime. You look at strategies to maximize the battery cycles and minimize degradation. That we've already mentioned, oversizing is expensive and undersizing gives you inadequate performance. Then, obviously, you can look at augmenting a battery in the future, which means that you can have a cheaper battery to start with and then add capacity later on in life as the shrinks and the capacity requirement increases. Then, obviously, there are a number of operational constraints and requirements. We're looking at depth of discharge, the charge-discharge C rates, the number of cycles per day, and then losses. I've put losses there in bold italics. People tend to ignore them, and then they are real, unfortunately. And if you ignore them, you can also run into problems. Obviously, we've already said there will be a number of use cases where you've got to consider the sizing, whether it's backup power, energy arbitrage, peak shaving. So you've got to tailor your storage capacity accordingly. And then as you dive deeper into the space, there are a number of modeling and optimization techniques that can give you good statistical and financial based sizing options. For example, the Homer software has got a variety of analysis tools that can help you to find an optimum battery size. All right, then I'm just going to do a quick sort of review of the considerations of economic matters. And obviously, you need to find the size of battery that delivers the best economic value. And I think that is what most clients would like to see. So if you look at a typical containerized base, I've just used some example here of, excuse me, the 500 kilowatt, 1.74 megawatt hour containerized system. You can see the cost of the battery part is about 75% of the entire system, with the remainder split more or less between the inverter and the AC cluster and the rest of the balance of plant, which includes the housing, the HVAC, fire suppression, and reticulation. So yes, there you can see that the battery cost itself has got the highest upfront expense. So it's obviously good to look at the size of the storage. So you've got to look at your levelized cost of ownership. I'm looking forward to the next presentation. I think we will be hearing more about that. I'm not going to cover that in detail. Then you obviously have to look at the other system components that contribute to the overall cost. Then something that often is left out is you've got to look at the ongoing O&M, the operator maintenance costs as part of your total expenditure. Because if you leave that out, you can get confusing numbers on the ROI of the battery. Then another part of it, but for this you need to talk to financial experts, but you've got to look at subsidies, tax credits, and other incentives that might be available that can offset costs. And obviously the financial modeling, and that can get quite involved if you look at the use cases of the batteries over 10 to 12 years. Then obviously again, we've got to look at the economic drivers for a specific project, and then you must determine the cost benefit ratio depending on the system use and the system sizing. Then obviously you start off with the capital cost, which is the initial investment. As we already said, you look at the operating costs, replacement and operation expenses. Then you must obviously look at how is this battery going to make you money or create savings. That is an important part of the ROI equation. Then you must also consider the degradation impact of the battery, because it does degrade over time, as previous speakers have already mentioned. So we need to keep that in mind. Then obviously you're going to look at your various ratios, your rand per kilowatt and rand per kilowatt hour numbers. Sorry, this is South African currencies, but yeah, you could just as well use dollars per kilowatt and dollars per kilowatt hour. So as some of the previous speakers already mentioned, if you look at strategies for extending the battery life, you can obviously also impact the sizing of your design. Now, it was already mentioned, if you look at the depth of discharge that you use versus the expected capacity, you can see that the curve there shows you that the deeper you discharge the battery, the cycles reduce. But again, this could be part of quite a complicated economic equation. But the fact is, the deeper you discharge, the quicker it will degrade. The other aspect that was also mentioned is the effect of temperature and the charge rate or discharge rate. So you can see if your battery is too cold or too warm, you can get a rapid degradation in the life of the battery. And also with a higher capacity. That's why typically we do not recommend you using a battery higher than 1C, ideally actually an half a C, which gives you an optimal lifetime on the battery. So another very important part, which was also covered in the previous session, is the BMS. The better your BMS, the better your battery will perform and the longer it will last. I'm not going to go into any detail, but it's a very crucial part of a battery system. And you've got to then look at managing your depth of discharge levels, thermal management. I cannot stress the importance of that. You've got to have a thorough thermal management system in place. And then obviously regular maintenance where you can identify and address potential issues early. And this would include simple things like cleaning filters for cooling inverters. If you don't do that, you will lose cooling efficiencies. All right, then we've also briefly talked about augmentation strategies. So if you can, it's good to look at a modular system where you can increase size as you go in the future. So you can add additional battery packs to increase storage capacity later on. This allows you to grow the system along your requirements, and you can also create efficient financial modeling. So yeah, to start with, you can reduce your initial capital investment requirement by deferring investments to a later stage. And that's again where usage and cash flow and things like that are important when you look at sizing a battery. We've already mentioned that a modular design in this sense is crucial, where you want to be able to add either strings or additional modules in your battery racks. And based on that, then you will have a scalable architecture which will allow you to grow the system as you need. And another very important part of this is obviously future increases in power demands. Also, as the battery gets smaller through fading with use, you might have to replace or add modules to give you your original capacity. We've already covered that. Then another thing which definitely is going to happen is that there are technology developments with upgrades that can increase capacity and efficiency going forward, and it might make sense to augment your older battery with newer technologies. As you can see there's an example of a Brunova rack which consists of modules, and we can enhance or augment the battery with adding new modules to this going forward or adding additional strings. And we're also looking at a few other initiatives around that. Okay, let's look at some use cases. Backup power, which used to be a big thing in South Africa with load shedding. For now, it seems to be history. Time will tell. But typically, what this does is it gives you uninterrupted power during outages, which is important for residential people in terms of convenience, and also very important for commercial and industrial users to ensure sort of smooth production and so forth. You don't want big power disruptions on your equipment. That is not good for the equipment. So typically when you look at sizing, you've got to look at the power demand for the required duration, so that you've got enough energy in your battery to supply the load during the outage. And then, of course, you've got to look at avoiding the cost that you can save from avoiding downtime and losses. Also, the cost of diesel. During the peak of the load shedding, people were spending huge amounts of money on diesel. Again, your load profile is important, where you need to look at your average and peak load so that you can make sure that there is enough energy in the battery. And as also discussed in the first presentation, if you have PV but the grid goes and you don't have a battery, you can't use the PV. So by looking at combinations of PV and generators, you can look at minimizing your base size to minimize cost, but still have reliable power with cost savings. Just one note, your inverter must be able to handle peak loads and reactive power. This, as the last question that came up was about, you've got to keep up with the inrush currents and so forth, and your inverter must be able to handle that. Then what you can do is you can also look at other use cases other than above backup that could enhance the value that the battery generates. For example, arbitrage. If you look at the energy arbitrage use case, that's quite simple. You can buy electricity when it's cheap and charge your battery with that, and then sell the electricity back when power is expensive, and you make a saving in that way. And also, if you've got PV in the middle of the day, which exceeds your load, you can use that to charge the battery for the evening peak cycle. So this is an area which I think is going to be quite active in the near future, especially as and when we move to dynamic tariffs, which I'm sure will happen in South Africa. At the moment, it's quite a thing in Europe and America and Australia. And as we get more and more PV in the country, I suspect we will reach the territory of negative electricity in the middle of the day. It would be great if you can charge your battery with that. So yeah, basically we exploit price discrepancies by buying low and selling high. We've already spoken about using PV during the day. And you typically in South Africa have 2 cycles per day, the morning peak and the evening peak. And then you've got to size your battery according to those periods. And now what you typically will find is that a battery that's optimized for arbitrage is similarly optimized for 2-hour load shedding sessions. Anyway, you again need to look at historical and projected energy prices, and then based on that, you can work out your ROI for arbitrage. And yeah, as already said, your BESS can be useful for backup as well if you've got a similar size, which will determine your sizing requirement for the storage part of the BESS. Okay, then I think just in conclusion and recommendations, including economic factors and strategies to extend the life. And obviously, by having optimal sizing, you can reduce your cost, improve your performance, and maximize your ROI. And just I think, if I may add this, a bit of advice. Talk to experts, people with experience, when you're looking at sizing batteries and so forth, because there are quite a few people out there that don't necessarily understand all the nuances and complexities of a battery system. So use a trustworthy supplier with a proven track record using world-class components and systems to ensure the longevity and reliability of your system, and also to make sure sure that it's bankable, because financing of batteries, bankability is important, and you have to be able to convince the financiers that your system is bankable. And then also don't underestimate the importance of a service level agreement. And you do need a good EMS to ensure that the economic benefits are realized. Beware of the quick buck brigade. There are many of these guys out there that are climbing on the bandwagon, selling batteries, thinking that it's like selling chips. And in actual fact, it's not. Then look at your partners. You've got salespeople, skilled, experienced people, and you've got trusted advisors. And if you've got a trusted advisor on your team, it will result in a pleasant, positive experience. All right, then I'm going to just give you one quick example of one of our recent projects, Midstream Estate in Centurion. We've installed 6 12-meter containers with 1 megawatt PCSs in each of them and 2.8 megawatt hours worth of battery. And this is supplying the residential and commercial clients in the estate for both backup and arbitrage and self-utilization of PV. You can see there's a 2.4 megawatt PV plant in the background, and there are days when there's excess PV, and that is then used to charge the battery. Integrated with generators, PV plants, both the big one you saw there, a number of smaller ones, and a number of small SSEGs that are in the estate. And it's tied up into the 11 kV network. And the main objectives of the site is cost reduction, reliability of supply, backup, and also black start. So we can black start the entire estate and give them power in conjunction with the PV and the generators if that is required. So just from a sizing point of view, why 2.8 megawatt hours of storage per container? So the intention is to be able to handle 2 hours of backup for arbitrage or load shedding. That requires 2 megawatt hours. Then you've got to add losses. In this case, we're looking at around about 6% discharge losses, which requires 2.13 megawatt hours of capacity. And if you only discharge to 80% depth of discharge, you need 2.66 megawatt hours. So in this case, there's around a 5% spare capacity, which is insufficient to compensate for state of health fade for around 2 to 4 years. And if by then the use case is still making sense, then there is room to augment the batteries by adding additional strings. So I think, John, that is my story. Thank you very much. And I'll take any questions.
Thank you very much, Carl. As always, very useful and very complete. And it's specifically on this topic, thanks to your presentation, we understand that every situation is different and every situation requires a close look and analysis. I'd like to ask you a first question about this. In the case study that you've just shown, obviously this was a relatively big installation with a, I assume, well-organized end user who probably had the technical capability to have this discussion with you directly. There's also many end users out there who are not as technically savvy. How do you work with them? Do you work mostly with the solar installer because this is the main point of contact, or do you try to work directly with the end user? And what would be your recommended approach for all the people who are listening here today, and most of them are professionals from the solar industry?
All right. So in the midstream case, we dealt with the end user directly. He's an educated, intelligent engineer, but he wasn't a battery expert. So that was part of our approach as being a trusted advisor, is that we engaged with the client and we walked the road together. It was a 6 months project in terms of requirement specification, getting the concepts documented, getting it implemented, doing a site acceptance test. So there was a lot of work to be done together with the client. If we talk about the PV installers and so forth, again, we've done quite a few projects with EPCs. And again, we would get to know the installers and form a relationship with them and assist them. And in time, they get sufficient expertise, they can be more independent. But if necessary, we engage with the EPCs and we will assist them with advice and so forth.
Quick question about no, first a comment about you had a graph there about the impact of the temperature, which is a concept that everybody knows, everybody talks about that. We know that we must not go too cold and not go too hot. But I was shocked by how quickly the life cycles drop as soon as you go out of a relatively normal temperature range. I don't think many people are aware that this is so dramatic. Um, are we talking about a permanent temperature at this level, or is there also an impact of if you have one case of one day of a very, very hot temperature or very, very cold temperature, it can also have dramatic impact?
John, I am not a serious expert on that matter, but what I can say is that if you try and charge a lithium battery at below 0 degrees, only once it will give you permanent damage. And if you try and run it at above 60 degrees, only once it will give you damage. I cannot quantify the amount of damage, but if you do this every day, you'll damage them much quicker. And I mean, you can imagine if you discharge a lithium battery to below 2.5 volts, which is basically empty, you also cause permanent damage, which also accumulates in time. So, excuse me, if you've got a decent BMS in your system, it will see the temperature is below, say, 0, and it will disable the battery. Or if it's above 50 degrees, it will disable the battery. It will actually prevent you from using the battery under those circumstances. But yes, damage will be done. And ideally, you want to keep your battery to around 25 degrees Celsius to optimize the life. And you also want to sort of minimize the spread between cells in your system. Otherwise, they age at different rates, and then you just create trouble for yourself going forward.
Very good introduction to the next question from Ozaji. So there was a little bit of unclarity in earlier discussions, I think, about can we add batteries to an existing system, yes or no? I think it's important to explain that with lithium, it's possible. And Ozaji is actually asking specifically about this in configuration of augmenting a BS solution by adding new batteries. While certain batteries may have lost capacity over time, does the round trip efficiency become the same, or does it get worse? And how does this impact any technical choice that you may make at the point of adding new batteries to your system?
That is a very complicated subject,
Ah,
complicated and complex subject. Because one of the consequences of a battery aging is that your internal resistance goes up, which increases losses at high rates. So that it definitely reduces efficiency. So if you put a new, let's say so let's, for example, say 5 years from now you want to augment an old battery. You can't find 280 ampere hour cells. You can only find 350 ampere hour cells. So the impedance of those cells are much lower. So you've got to look at the complex dynamics of system impedance and power sharing and so forth. There are a number of augmentation strategies, and I think that would be a presentation on its own, where you can look at adding modules to existing strings, or you can look at adding new strings. You can look at mixing old modules and new modules in different strings. And then you can also introduce other forms of technology to allow you to have newer technology batteries working with older technology batteries. But it does not necessarily mean they all go on the same DC bus. But yes, you can. And typically, if we have, like in the midstream case, if the battery is less than 2 years old, we can add new strings in parallel to the old strings, and it will balance itself out, and you will have a fairly efficient, useful battery life going forward. The new strings will work a little bit harder. The old strings will work a little less hard, and in the future they will converge to work equally.
Thank you. And if you'll allow me one last question, a question from Carlo, specifically about what you mentioned on energy arbitrage. Um, so the assumption here is that dynamic tariffs will come soon to South Africa. Um, and the idea of the question is like, how does that impact the sizing of storage on projects? Or maybe better said, what is your expectation of the impact on the sizing? What do you think people will start doing? Will they massively start installing storage to try to play on the stock market? Or are they going to be reasonable and take this energy arbitrage as a small bonus on the side?
Look, in Australia and in America, it's already quite a strong driver for business cases. And the sizing will obviously depend on the economics of the situation. But for example, at the moment, Eskom has a number of wind farms supplying power to the grid. And if the demand is less than what is available, they ask these wind farms to curtail their production, and they still have to pay them for the electricity they would have taken or could have taken, but they don't because they don't need it. So that effectively means Eskom is paying for something which is not getting. Now, if you made that power available to people at a reduced rate to charge their batteries with, it will make a big sense for them to use that power, charge their batteries, and then sell it back to the grid when it's needed. And typically, I think at the end of the day, sizing will play a role, but typically you have to look at the future of what the impact of PV and wind will be. So you'll typically have the peaks in the mornings and the peaks in the afternoons. So your sizing will probably be driven by that in terms of the energy that you want to sell. And yeah, there are complex, sophisticated AI tools out there nowadays that can predict these things and help you maximize your profit. But yeah, in South Africa, that's not here yet. It will come soon.
Well, thank you so much, Carl, for sharing some of your knowledge with us today.